For our project, we took a road trip and measured the distance every 60 seconds. As we were leaving, Ricardo accidentally left his backpack on top of the car. Ricardo watched the time and called out every 60 seconds. When Yusuf heard him call out, he announced the trip meter reading and reset the trip meter.
Time 2, 1, time 3, 1.3.
They continued taking time and distance data until 7 minutes into the trip, when Ricardo remembered leaving his backpack on top of the car. They turned around to get it. As they tracked the distance, their displacement is now negative. 13 minutes into the trip, they find the backpack. Ricardo picks it up, and they turn around again.
I took the time and distance numbers from Ricardo and made a graph.
Okay, this is the time from our road trip, the distance from the last minute that we took from our time. This is the area that we turned around, and you can see that's positive here but negative here, and this is our total displacement. So this is the plot of our data points. We have our equation of regression, and our graph, the dotted lines show the actual equation, which is a really good fit besides the first couple minutes, which is kind of off. So our y-axis is the displacement in quarter miles, and our x-axis is in t minutes. And the square points is mostly from our raw data that we got. Okay, so this is my graph of our displacement equation, or displacement graph, and this is our equation of regression. And just to point out that our first couple minutes are off, and so our displacement is in quarter miles and our minutes are t minutes, and so we are increasing here, and at this point we have to turn around and go back for our backpack, so it's turning negative, and then again we turn back around to go forward and we start increasing again.
Okay, I took the displacement equation and I took the derivative to find the velocity of the car. I set the velocity equation equal to 0 to find the critical points. Using the increasing and decreasing test, I found a local max at 6.8 minutes and a local min at 13.2 minutes. And with this information, I made a velocity graph. The velocity is positive and decreasing when the displacement is increasing and concave down. The velocity is negative when the displacement is decreasing. The velocity is positive and increasing when the displacement is increasing and concave up. Then we got two critical points, one at 6.8 when we turned around to get the backpack, and the second critical point at 13.2 when we turned around again.
Okay, so once we found the velocity equation, we can go ahead and find the acceleration equation by simply taking the derivative, which is going to be equal to 29 over t minus 29. So once we found the acceleration equation, we can go ahead and set this equal to 0. And once we set equal to 0, we're going to find out that t is going to be equal to 10. At t equals to 10, we know then acceleration is gonna be negative over here and positive over here. So that means that at t bigger than 10, velocity is gonna be positive, it's gonna be increasing. And then when t is going to be smaller than 10, our velocity is going to be decreasing. Okay, the first graph represents the displacement graph, where it goes when the car travels from 0 to 20 minutes. And once we set this equation, once we take the derivative, we find the velocity. Here's the velocity graph. And once we set the velocity equal to 0, we find the two critical points, which are 6.8 and 13.2, which represent a local max and local minimum on the graph. And also from the velocity graph, we can tell a difference between distance and displacement. Distance is the area absolute value of each part in this graph. Instead, displacement is only the area, the positive area. And then, from the velocity, we can find acceleration, which is the derivative of velocity. And once we found this equation, we set it equal to 0, and we found t equals 10. And t equals 10 is an inflection point when the curve on the displacement graph goes from concave down to concave up.